ultimate search for cosmic company. I'm here to talk today about how we hope that we can realize that wish. So let's get started. So most of these figures will probably look familiar to this audience. I put them up here partially because working in the details, as some of us do, you tend to lose sight of how extraordinarily large the repositories of data that we're responsible for are. But I also want to bring into perspective two of these numbers. The first one, 750 gigabytes, is the total amount of storage that all of our observations to date would consume had we been able to keep them all. Now, 3/4 of a terabyte doesn't seem like anything by today's standards, but in the early 90s, when we were developing the Phoenix system that we were observing on, a gigabyte per day, the data stream at the time, seemed like a tremendous luxury. So we had 4 1-gigabyte drives, and at the end of the 4th day, we'd throw away the data on the first drive and recycle it, and that data was gone forever. And I often wonder what kinds of new results we might be able to derive from that data had we been able to keep it and reanalyze it today. But we'll never know. The second number, 918 exabytes, is the amount of storage that we will consume in 1 year, 5 years hence. And this is really my problem. So hold on to that thought for a moment while I walk you back through a little bit of the SETI Institute's history. The SETI Institute was founded in 1984 to explore, understand, and explain the origin, nature, and prevalence of life in the universe. Now, when most people think of the work that we do here, they picture Jodie Foster sitting in front of a bank of computers with a pair of headphones on. And of course, that's not how it really works. Jodie Foster never shows up for work anymore. Just too big, I guess. But more importantly, radio astronomy that's depicted in this movie is just a tiny part of what amazes me and fascinates me about the SETI Institute. Folks are often surprised to learn that we also study astrobiology, of which the radio search is a part. And astrobiology is the study of little critters out there in space. We also do planet finding, and some of you may have heard of the Kepler mission that's about to launch next week. We've got principal investigators involved in that science as well. We have a full high school curriculum for science, and we have a summer program for undergraduate students. So with 150 employees, the SETI Institute is a buzz with cutting-edge research into all aspects of the study of life in the universe. So Project Phoenix was started. It was the first privately funded SETI search at the SETI Institute, and it was started in 1995 at Parkes Observatory in Australia. From there, it moved to Green Bank, West Virginia, to the NRAL, and in 1998, we moved to the world's largest radio telescope at Arecibo, Puerto Rico, and we stayed there for the next 6 years. Throughout the decade that Project Phoenix observed, we were never able to secure more than 50% time on our instrument. And at Arecibo, it was down to 11%. I remember in these years of observations this kind of frantic, focused, and exhausting rush leading up a few months before an observation. And then 3 weeks of sleepless nights while we observed. And then it all just turned off until we had to warm up for the next observation. And it was clear to me, as it was to everybody in the team then, that if we wanted to improve our chances of success, that we would have to have access to full-time observation on some instrument. So, in 2005, with the generous support of private donors, including Paul Allen, we began R&D on the Allen Telescope Array. This large array of 6-meter dishes would allow us to do observations year-round. But in addition to that, it would also give us a much larger field of view than any other instrument that we had access to. In fact, I believe than any other instrument in the world. And it has a much larger bandwidth. And all of this equates to big wins for science, and of course, big headaches for IT. Today, the instrument boasts 42 dishes and is in the early stages of SETI observations. Within 5 years, with proper funding, we will be fully actualized with 350 dishes. And we'll be doing SETI observations nearly every day of the year. Now, one might forgive us for resting on our laurels at this point. After all, we have just now logarithmically increased our chances of success. But that's not how we roll. So, under the guidance of Sunzone Greg Papadopoulos, we spec'd out the next generation of SETI observation equipment. It's called the SDRT, Software Defined Radio Telescope. I like to think of it as SETI for the people. The core principle of the SDRT is to open source the mechanics, data, and algorithms of the SETI search so that anyone with expertise or even interest can participate. Oh, and improve the system, of course. With the SDRT, we'll be able to bring this compelling search to computer scientists, mathematicians, faculty, staff, students, and even my grandma. iSETI, which is one proposed use for the SDRT, will use our innate pattern recognition skills to extend this search to anybody that's interested in possibly near real time with very little training. Crowdsourcing SETI will lead to new algorithms, technologies, and results. And from these, we'll select the best of the best to roll into our production system. Which brings me back to our problem. 500 megahertz, 2 polarizations, 8 bits per sample, 2 samples per time slice for NiQuest, times as many antennas as we can get our hands on. We have 42 now, and we're working our way up to 350. So in the near term, we'll be pulling 500 megahertz from 42 dishes. Every day, this will generate roughly 300 petabytes, and by the end of the terabytes, and by the end of the first year, 100 petabytes. And we're going to have to put that somewhere if we're going to get it out to people. So these numbers, incidentally, are in metric units, and of course they'll appear different when they're translated into binary, but it's a lot easier to work in binary, and it's still a lot of bytes. So you might ask if there are alternatives, and of course there are. We could, instead of taking that raw data before it gets formed into different beams and fields of view on the sky, we could take it after that. And by our current estimation, we'll have 3 beams. So we'll go from 350 antennas down to 3 beams. The problem with that is that it will cost us about 20,000 possible recombinations of that data later. So the beams that we select on the sky now may not be the ones that we want to go back and look at in the future, and we won't have the opportunity to go back. That's more missed opportunity as far as we're concerned. So why should we store the raw data? Well, storing raw sky data allows future generations to look at old data and apply new technologies to derive new results. And obviously, for some of the reasons that I mentioned already, this is important to us. But similar archives have also been done in the optical astronomy domains. First at Palomar Observatory in the 1950s, and then later at the Apache Point Observatory with the Sloan Digital Sky Survey. Now, these surveys have been used by astronomers for decades, and they serve as a vital reference point to our cosmos. The virtual time machine that they provide allows today's scientists to peer back into the past and correlate current celestial events with the unnoticed events of yesterday, and hopefully deriving new results out of that as well. So the SDRT will provide the same kind of data survey in the radio frequency domain, which, as far as I know, has not happened yet. So in 5 years, we'll be pulling 500 megahertz from 350 dishes. We anticipate a capacity need at that point of 2.5 petabytes per day and nearly a zettabyte per year. And if anybody in this room can help me wrap my head around a zettabyte, I'd really appreciate it, because it's out of my scope. So that's where we're headed and where we stand today. And I'd like to leave you with this to think about. In the middle of the 15th century, when global exploration was tantalizingly within our reach, a few brave and incredibly well-supported individuals led Western civilization on a voyage of unimaginable discovery. And today we stand similarly situated, tantalizingly close to discovering our place in the universe. In the next 5 years, Moore's Law will exponentially accelerate our search. By 2025, we will have scrutinized 1 million stars. That's 1,000 times the number of stars that we've been able to look at in our entire history. Oh, according to the Drake's equation, This number, 1 million stars, is enough to yield at least one confirmed alien civilization, and possibly many more. Today, I invite you to participate in this extraordinary search. There are a multitude of problems that need solving. Capture, transit, and storage of hundreds of gigabytes per second is a daunting task for the best of us. Getting that data out to the world without breaking the bank is, for a small, privately funded nonprofit project, a real obstacle. If you think that you might be interested in participating and helping us to solve these technical, social, or funding problems, please stop by after my talk or later on this evening at one of the social events, and I can help find a way for you to participate. Thank you so much. And at 11 minutes, I think we may have caught up.
Yes, we have. Thank you.
So I'm going to put up also our needs while we're taking questions. You guys can peruse this, and there's a link to Jill's website on the slides. Questions?
Ken Santoros at Microsystems.
Hi.
You know, you're talking about zettabytes, et cetera.
Yep.
At some point, you know, you do the rough mental calculation of how much that's going to cost you. So you've got your hands around that and the ability to go ahead and fund those kinds of things.
Well, to some extent, we have our hands out. We're looking to the industry leaders, people who have access to these kinds of data stores. We've talked with Amazon, with Sun, with Google, and we're going to be talking with anybody that is interested in participating. I gave 3 different examples that we could execute on. Current data rates are much more reasonable. We're only pulling today 70 megahertz. And so if you reapply that algorithm, you're going to come up with maybe a couple hundred gigabytes per day. We are hoping very shortly to overcome that, move up to 200 megahertz within the next, say, month or so. Maybe next few months. I don't want to push our staff too hard. And then 500 megahertz within the next year. So we're incrementally addressing this issue. And initially, I think we're going to have slightly more tenable goals.
During the TED talk, she had one example. She talked about so far that only explore about the 1 glass of water of the whole ocean, and then won't use this to say, well, it's no life in the ocean. For average scientists or the staff in the study, what's your expectation? How soon we can find the other living organization in the universe at the current pace?
That's a very good question. All right, so I'll repeat the question. The questioner asked, or reminded us of Jill Tarter's quote that to come to the conclusion that there is no life in the universe based on the studies that we've done so far is like dipping a glass into the ocean and seeing no life in it and coming to the conclusion that there is no life. We feel that that's an absurd conclusion to come to, even though in the last 20 some odd years we haven't come to a positive conclusion. And the question is, when do we expect to find something? Now, I can no more answer that than any of you could, but our speculation, as I alluded to, is that by surveying as many stars as we can and getting up to that maybe 1 million star number that we're hoping to be at 2025, that we will dramatically increase our chances of running into extraterrestrial life. So if I had to just pick a number out of a hat, I would say 2025 is where you put your money.
I'm just curious, using the example that he was given with the glass of water out of the ocean, why would you necessarily want to analyze more of the ocean? How do you know that the answers you have aren't in the glass that you have, and you just need to throw more processing power at the current data set? Which is to say, how do you know what you're looking for, and how will you know when you find it?
That's an excellent question. So different people in my organization will give you different answers. There's two people that I've heard give this answer that I have a ton of respect for, and in a lot of ways I'd like to defer you to Jill or Seth, who can answer this question probably much more eloquently than I can. But my own personal view on this is that there are two factors. First factor is what we know. We can't search for things that we don't know about. It's just not scientifically possible, and we're a scientifically based organization. So we know about radio frequency, and we know about optical frequencies. And so we're doing searches in both of those domains. Now, the most common and most popular, and the one that's done the most work on, is radio frequency. And what I believe is that as a civilization evolves, it doesn't necessarily shed its old technologies. I mean, we haven't given up pen and paper yet. And I don't think that that's ever going to happen. And I think that radio frequency, in much the same way, is with us to stay. And the amount of radio frequency that we pour out into space is tremendous. And you need radio frequency to do almost every kind of science that's ubiquitous in our world today. Whether you're talking about nuclear science, or radio and television broadcasting, or communications, even our Ethernet has RFI, and all of that gets pumped out into space. So the question, in my mind, is not, will another civilization use that? Of course, there's theoretical types of creatures that could communicate telepathically or what have you, but would they shed that over time? And I believe they would. And I believe that with any luck, they'll be loud enough as we are and pollute the RF spectrum enough that we'll catch them.
Just a compliment from the web stream. Neil Heather says that you're doing a fantastic job.
Thank you.
Hi, I have a question. After Card said that needs sufficiently advanced technology is indistinguishable from magic, you think that any sufficiently advanced communications, radio communications technology through use of things like CDNA or encryption or compression would be indistinguishable from white noise? How do you think it would?
That's a good question, and again, I'm going to defer in large part to folks that know a lot more about RF than I do, but I will say this. The current algorithms that we're using, we use continuous wave detection and pulse detection. They don't care about content, so frequency hopping and other spectrum games that you can play, they don't affect our ability to interpret those kinds of transmissions. Now, you may be alluding to something that, again, we don't know about yet, and I can't obviously formulate a hypothesis for how to study or search for those kinds of signals. But if it's along the same lines as our technology, we should pick it up. Now, SDRT and this idea of SETI for the people is another way that we address that. There's a lot of people out there that have a lot of time and a lot of know-how that can take what we've started and extend it. And with this data being available on, I don't know, Amazon or Google's servers or whoever's, they can get the data in hopefully close to real time and do the same kind of science we're doing. Now, additionally, we can take this data offline and do searches that are much too costly in CPU hours to do now in real time. And so in both of those ways, I can foresee overcoming that hump of what if they do this or what if they do that. We can just start cramming more and more algorithms into the back end that can make that more feasible.
All right, if there are no more questions, we will break for coffee now. Thank you very much, Tucker. It's
Thank you.
been wonderful to have you here.